April 1957. Inside a loud, fluorescent-lit engine lab in Detroit, a group of Chevrolet engineers stood around something that didn't look revolutionary at all. No massive displacement, no exotic aluminum heads, no supercharger whining on top, just cast iron, just 283 cubic inches, and yet, within months, this little V8 would quietly change the future of American performance forever. But what almost nobody knows is that this engine wasn't supposed to become a legend. It wasn't designed to dominate drag strips or terrorize NASCAR. In fact, when development started, it was meant to be a modest evolution, nothing more than a slight improvement over the existing 265 small block. A bigger bore here, a revised cam profile there, maybe squeeze out another 15 horsepower for the marketing department. That was the plan. Instead, what happened next kicked off the horsepower wars that defined the entire muscle car era. Most people think muscle cars were born in the mid-60s. The GTO, the 442, the Hemi. You think you know this story? Not like this. Because the truth is, muscle cars didn't start with big blocks. They started with 283 cubic inches of small block rebellion. By the mid-1950s, Chevrolet was already under pressure. Ford had its Y-block V8. Chrysler had the firepower Hemi. Both companies were building reputations around raw power. Chevrolet? It had just introduced its first small block in 1955, the 265 cubic inch V8. That engine used a 3.75-inch bore and a 3.00-inch stroke. It made around 162 horsepower in its base configuration. Respectable, but not exactly terrifying. It was smooth, it was efficient, it was modern for its time. But in the parking lots outside diners and drive-ins across America, kids weren't talking about efficiency. They were talking about who could blow whose doors off. And inside GM, there was growing concern. Performance mattered now. NASCAR mattered. Drag racing mattered. America's highways were filling with bigger, faster cars, and the brand that built the most powerful engine would own the imagination of an entire generation. Chevrolet's chief engineer, Ed Cole, understood this better than anyone. He knew the 265 was a good start, but it wasn't enough. Not if Chevrolet wanted to compete, not if they wanted to win. So, Chevrolet engineers went back to the drawing board. They kept the 3.00-inch stroke from the 265, but they punched the bore out to 3.875 inches. That doesn't sound like much, an eighth of an inch. But mechanically, it changed everything. Displacement jumped to 283 cubic inches. Cylinder wall thickness became dangerously thin. Go any further and under load, those walls would crack. Oil consumption would spike. Blow-by would kill compression. They were right on the limit of the casting. The foundry engineers warned them. "You're pushing it," they said. "The casting process can't guarantee wall thickness consistency at these tolerances." But the performance team didn't back down. They ran stress tests, thermal cycle analysis, measured everything down to thousandths of an inch, and then they decided to push it even harder. The new performance version ran an aggressive 9.5.1 compression ratio. Cylinder heads were redesigned with improved valve angles for better flow. The intake manifold was optimized for high RPM breathing. With a 4-barrel carburetor, it made 220 horsepower. That alone would have been impressive. But with dual 4 barrels and a hotter camshaft, that number climbed to 270, and suddenly, transmissions started failing, drive shafts twisted, clutches slipped, gearboxes shattered under load. Test drivers reported that during full throttle acceleration tests, you could actually hear the drivetrain screaming for mercy. One engineer later recalled, "We built an engine the rest of the car wasn't ready for." So they went back. Reinforced transmission cases, upgraded clutch materials, strengthened U-joints. But Chevrolet wasn't done yet, because in 1957, they did something that had never been done before in an American production car. They gave the 283 mechanical fuel injection. Not a carburetor. Fuel injection. The Rochester ramjet system delivered fuel directly into the intake runners with stunning precision for its time. Designed in collaboration with General Motors Research, it used a complex system of mechanical linkages and fuel distribution to meter fuel with unprecedented accuracy. No fuel slosh, no starvation in corners, no hesitation off the line, just clean, immediate throttle response. Each intake runner received its own precisely metered fuel charge. The system adjusted for throttle position, engine speed, and load. It was a marvel of mechanical engineering at a time when computers didn't exist in cars. With that setup, compression rose to 10.5.1. Horsepower? Exactly 283. 1 horsepower per cubic inch. Today, that might not sound like much, but in 1957, it was unthinkable. A production V8 that made 1 horsepower for every cubic inch of displacement had never existed. European exotics couldn't even claim that. Ferrari's race engines barely touched it. Mercedes-Benz 300 SL? Close, but not quite. And here was Chevrolet, an American mass-market manufacturer, achieving it in a production engine you could order straight from the factory. And suddenly, the entire industry was on notice. Ford's engineers reportedly obtained a fuel-injected Corvette within weeks of launch. Tore it down, studied every component. Chrysler did the same. Because this wasn't just impressive, it was embarrassing to the competition. At the drag strip, the impact was immediate. A fuel-injected 1957 Corvette equipped with the 283 could run the quarter mile in about 14.0 seconds at nearly 100 mph. That was quicker than most big lumbering V8 sedans running far larger engines. Pontiac's 347 cubic inch V8? Slower. Oldsmobile's 371? Couldn't keep up. Even some of Chrysler's Hemi-powered machines struggled to match it. And it didn't just win races. It embarrassed rivals. Street racers loved it. The engine responded instantly. Peak power came on strong at 6,000 RPM. And because the entire package was lighter than big block competitors, weight distribution improved handling. You could out-corner them, then out-accelerate them on the straights. But there was a problem. At sustained high RPM, above $6,000, oil pressure dropped sharply. Bearings overheated. Mechanics began reporting that after long pulls, the rod bearings looked scorched. One crew chief later said, "They came out looking like charcoal briquettes." Why? Because the original oiling system fed the camshaft first and the crankshaft second. At high RPM, that meant the most stressed component in the engine, the crank, was getting oil last. Oil starvation at the mains and rods meant metal-on-metal contact, friction, heat, wear, and eventually, catastrophic failure. So engineers revised internal oil passages. They improved flow priority to the main bearings, increased oil pump output, strengthened the crankshaft journals, added windage trays to prevent oil from whipping into foam at high RPM. It wasn't glamorous work, but it meant the 283 could survive something new, continuous abuse, and that changed racing forever. Stock car teams began experimenting with it in NASCAR competition. And despite its smaller displacement, the engine's ability to rev reliably gave it a unique advantage. While larger engines struggled past 5,500 RPM, the 283 could push towards 6,200 with the right camshaft. More RPM meant more power, without increasing displacement. Smokey Yunick, the legendary NASCAR mechanic, saw the potential immediately. He began building 283-powered Chevrolets that could run with, and sometimes beat, cars packing 50 or 60 more cubic inches. At Daytona in the late 1950s, teams running high-performance, small-block Chevrolets began posting shockingly competitive lap times. On tighter circuits, the lighter weight of the small block improved front-end balance. Less understeer, faster corner entry, better tire wear over a full race distance. And suddenly, brute force wasn't everything. Handling mattered. Power-to-weight ratio mattered. Engineering mattered. Then came drag racing. Hot rodders quickly discovered that the 3.875-inch bore allowed for larger intake valves and better airflow than the 265 ever could. With aftermarket camshafts, higher compression pistons, and open headers, modified 283s were pushing well beyond 300 horsepower. Some radical builds, with ported heads, radical cam profiles, and custom tuning, approached 350 horsepower. From 283 cubic inches, naturally aspirated. In cars weighing under 3,200 pounds, that meant quarter-mile times dropping into the mid-13s, at over 105 mph. In the late 1950s, cars that looked stock, sounded stock until you nailed the throttle, then screamed like nothing else on the street. And here's where things really changed, because the 283 proved something fundamental. You didn't need massive displacement to make serious power. You needed airflow, compression, RPM. It was a shift in philosophy. Instead of building bigger engines, engineers started building smarter ones. The 283 introduced concepts that would define performance engines for the next 2 decades. Free-flowing cylinder heads, high compression, aggressive cam timing, lightweight rotating assemblies that could handle sustained high RPM. High-revving small blocks became the blueprint for future performance engines. The later 327, the legendary 302 Z28 engine. Even the 350 that would dominate performance cars for decades. They all trace their DNA back to this one experiment in 1957. The 327, introduced in 1962, used the same basic architecture, but with an even longer stroke. It made up to 375 horsepower in fuel-injected Corvette trim. The 302, built specifically for Trans Am racing homologation, revved to 7,000 RPM and powered the first-generation Camaro Z28 to legendary status. The 350, which arrived in 1967, became one of the most successful engines in automotive history. Millions produced, decades in production, all of them children of the 283. But success came with consequences. Insurance companies began noticing that Chevrolets equipped with high-performance small blocks were involved in a disproportionate number of high-speed accidents. Young drivers, powerful engines, not always a great combination. Premiums climbed. By the early 1960s, insuring a young driver in a fuel-injected Corvette could cost hundreds more per year than a standard sedan. In some states, insurance companies flat-out refused to cover them, and regulators started paying attention too. High-compression engines required premium fuel. Emissions were higher. Fuel economy was worse. As the decade wore on, pressure mounted for cleaner, quieter, more efficient designs. Environmental concerns started creeping into the conversation. Noise ordinances, targeted open headers, and glass-pack mufflers. Smog became a serious issue in cities like Los Angeles. The golden age of unrestricted performance was already facing headwinds. But the cultural damage had already been done, because by then, America was addicted to horsepower. Chevrolet produced hundreds of thousands of 283 engines between 1957 and 1967. They powered Corvettes, Bel Airs, Impalas, Camaros, and Novas. They found homes in everything from family sedans to purpose-built race cars. In base 2-barrel form, they made as little as 185 horsepower. In fuel-injected performance trim, they pushed past 283. Affordable, durable, easily modified, they became the engine of choice for a generation of racers, tuners, and street performance junkies. Junkyards filled with them, speed shops stocked parts for them. Magazine tech articles taught readers how to rebuild them in their garages. You could buy a worn-out 283 for $50, spend a weekend and a few $100 rebuilding it, and have a screaming performance engine ready to drop into anything. And by the time production finally began winding down in the late 1960s, the blueprint for the muscle car era was already written. Higher revs, higher compression, better breathing, more power from less engine. The big block era that followed, the 396, 427s, and 454s grabbed all the headlines. They made the magazine covers. They set the drag strip records. But they were just doing what the 283 had already proven possible, making horsepower through engineering, Through airflow and RPM and efficiency, the big blocks just did it with more displacement. That 283 didn't just power cars, it changed how America built them, because without it, there's no 327, no 302 Z28, no screaming small blocks dominating Trans Am. Muscle cars might still have happened eventually, but not the way we remember them. Not with that same high-revving fury, not with that focus on power-to-weight ratio, not with that obsession over squeezing every last horsepower from every cubic inch. The 283 taught an entire industry and an entire generation of enthusiasts that bigger wasn't always better. Sometimes, smarter was better. In the end, the Chevy 283 small block wasn't the biggest engine of its time. It wasn't the loudest. It wasn't even the most powerful by the mid-1960s. But it was the first to prove that horsepower wasn't about size. It was about engineering. And that one lesson changed everything. If you enjoyed this story, let me know in the comments what engine you want to see next. Another small block legend, a forgotten big block, or one of the rival V8s that tried to take this one down. Was it Ford's 289 high performance that battled the 283 in the early 60s? The legendary Chrysler 340? Or maybe the Pontiac 326 that started its own revolution? And make sure to subscribe, because the next story might just change the way you look at performance forever.